In this video, we are going to go over elastic potential energy. The potential energy is stored in elastic objects when they deform. Elastic objects like rubber, like a spring, when you make a deformation, they go back to their initial state. Here I start with a spring. The spring at its relaxed point, when it's not extended or compressed. Force extension graph is a very useful graph to find that elastic potential energy. This force is a reaction force of the spring when it's deformed, and x here is extension. Here I extend it for a length of delta x. Force versus x, basically when the spring obeys the Hooke's law, is a linear graph. And now, as the extension is delta x, we expect the reaction force of F equals K delta x. K is the elastic or spring constant. It's a constant highly affected by the physical properties of the spring, like the form of the spring, its thickness, its material, and so forth. Okay, anyway, the area under the graph, under the Fx graph, is the work done against this deformation. Actually, the spring won't let you to extend it or compress it. You have to do some work against its reaction. The work done here is the area under the Fx graph, and it's very easy to find because the horizontal line, the horizontal side of this triangle is the delta x, and the vertical side, as you see, is K delta x. So the work done here is going to be height K delta x times base delta x divided by 2. So the work done is a half of K times delta x squared. This is exactly the energy stored in a spring, and it's called the elastic potential energy. A half of the spring constant times deformation. Deformation to the power of 2. This is just provided the spring obeys the Hooke's law. I mean, force extension graph or force compression graph is a line. I will add a very small notification here. You know that this x here is extension, but it could be also compression. Springs can have the same graph according to compression you make. So delta x also could be compression. It doesn't matter if you extend it rightward or compress it leftward. Anyway, you have to do this work, and the potential energy stored in the system will be the same. A spring of a spring constant 48 Newton per meter is extended for 0.4 meter. So the spring constant is 48 in SI units, and extension delta x is 0.4 meter. Calculate the elastic potential energy stored in the spring. I use the formula a half of K delta x squared, all in SI units, 48 for K, and here 0.4 for extension. The answer is 3.8 joules. An object of mass 0.78 kilogram is attached to a spring of unstretched length 560 millimeters. So this is the unstretched length, 560 millimeter. When the object has come to rest, the new length of a spring is 620 millimeter. Okay, I attach the object, it comes to rest, and this is 620 millimeter, the new length. Okay, calculate the energy stored in the spring. This is going to be the elastic potential energy as a result of this extension. Okay, let's start from the formula. Of course, you know that if you subtract these two, you will get the extension of 60 millimeter, or 60 times 10 to negative 3 meter in SI units. I start from the main formula, a half of K delta x squared. I have a challenge here. Delta x is given, it's here, but I don't know anything about the spring constant. A very easy approach is this. Let's decompose delta x squared to delta x. Mathematically, it's the same, but it has benefits. K delta x here is exactly mg. Why? At this point, the object is at rest, so it's in equilibrium. The downward force of mg is cancelled by an upward force of K delta x, the spring force. elastic force, K delta X. Now they are equal, so instead of K delta X, I can put mg. That's all. I know the mg, so I should easily find the answer. Of course, here I have taken the g to be 10. Okay, this is the mass, this is the g, and here I have the extension in meter. I've converted to SI units. So the answer is 0.23 joules. This is the elastic potential energy saved in the spring due to this extension. Thank you for watching this video. See you soon.